and I'm also chairing TeraFlowSDN software development group. So this tutorial will be a little bit more academic than what you have seen before. So my intention is not to give you a demo or a hands-on tutorial where you see TeraFlowSDN. We have done this many times. So we decided that maybe we had the chance of doing something different. So what I wanted to show you today is about a journey that we have started and that we need. Yes, this is me with AI, sorry. I couldn't avoid it. But the objective was to look for the Holy Grail. So that's me in the Nations look. And the Holy Grail for us is to have an autonomous network. So this tutorial is about setting the foundations on how TeraFlowSDN is doing this work. It tries to build autonomous networks. This you will see it's a challenge and it's a very long journey. We have not reached there yet, but I will give you during this hour and a half some of the hints and some of the different topics that we are doing and that TeraFlowSDN is contributing for having this view. And at the very end, we will see how far we are from there. So as you see, I always like to talk about three set networks. To have a fully automated network is about zero weight, zero touch, and zero trouble. So these are the three sets that are our objective. And of course, then for this, we need a lot of self-X networks, self-configuration networks, self-healing networks, self-optimizing networks, self-evolving networks. So a lot of autonomicity needs to be bring into the networks. We started the journey like 20 years ago about network programmability, setting up what was SDN, what was to support the control plane and the data plane, the coupling and so on. But then we need more. This was the foundations. We have a network that we can program. Now with the AI, we have seen that it's becoming more a reality to have autonomicity in our networks. And that's what we will be talking about, the different enablers for that. So I will be talking for an hour and a half, and the journey is quite long. We will start focusing on autonomicity and how we measure autonomicity. I will give you also some glimpse of the latest white paper at ETSI on network autonomicity. This is the first part of the tutorial. Then the second part is, okay, that's very nice. And what has, but you will have the question, what has TeraFlow to do with all of this? Then I will show you how TeraFlowSDN is impacting the different enablers. The enablers, you will see the spoilers here, the digital twin, the generative AI, AI agents, and the necessary data models. Then I will introduce you a little bit about the security and privacy. And finally, I will turn around a little bit the words, because all the talk will be, and all the tutorial is about AI for networks. But the last part of the tutorial, I will say it the other way around, networks for AI. TeraFlowSDN is a network enabler, and you will see that AI, as it is, it requires a new way of handling the network. So I will also comment on a little bit on how the TeraFlowSDN is supporting this view of networks for AI. Before starting, if you admit I'm burning here, so I will take out my American and now that we have this. Okay, so this the next slides, if you want to read it better and better explained than by myself, there is a white paper that I encourage you all to read. It's this called AI in the Evolution of Autonomous Networks. This is something that ETSI has done at a very global perspective, so involving all the different technical committees and also ISGs and SDGs, of course. So we have tried to contribute here, and everyone has positioned itself on the view of network autonomicity. I will start with the role of this artificial intelligence in an evolution. If you remember, I have been talking you about self-X networks. So here you have some of them. the self-configuration, where you need to detect the devices and understand which devices, which data models, whatever you need to integrate into your network, and how you configure it. So this is one part, very important. We need new devices. We need to plug them into the network. We need to self-discover them. We need to minimize the troubles, the zero-touch service management, and so on for all these devices. So we plug and play, just like that. Self-optimization, okay, this means that we have a network which is able to understand itself, it's able to measure itself, and to propose these ways of improving the resource utilization, for example, optimize the routing, allocate the resources, and so on. So this is also a very important part of this evolution that requires autonomous networks. Self-healing. So not only we want to optimize a network, but if we detect that something crashes, we want to automatically fix it with zero downtime. This means redundancy, but this also means minimizing the MTTRs and all these nice metrics from the people from the CTTC movement. Then we have the self-protection. This is not the same as self-healing. The self-protection is active healing in the sense that, okay, we are able to analyze what's happening and prevent, being more proactive to prevent from the need of healing. So we prevent the crashes, we prevent what will happen, and we act before it happens. This is very nice, and this is where most of the hyperscalers are right now. So you will see later that we have a way of measuring all this, and this is self-protection is one of the things that are needed right now to have this complete autonomous network view. And finally, the self-learning. You have seen some papers of Asians that include DRL in order to self-optimize themselves. This is the foundations of the self-learning mechanisms that are needed for this autonomicity. And I will also talk a little bit about this. So I think that I have motivated enough what we need. Now let's see how we can measure it. I think it's very important if you want something to become a reality, is a way of being able to analyze the different steps that are needed to become this reality. In this case, you see the different levels that TM Forum have designed in order to evaluate the maturity of a network towards the autonomicity of it. So we go from level 0, of manual operation and maintenance. That's what it's there. And you can see that, for example, we have different access in the figure. I don't know if you see my pointer. No, well, it doesn't matter. I cannot get up because if not, I'm not recorded. So let me see. It's down there. You see the different topics: execution, awareness, analysis, decision, intent. These are the different levels that help us to have this. Pointer. Thank you very much, Manel. Oh, it's here. You see that, okay, in manual operations, we have a system that requires manual execution. The P stands for personal, and the S stands for system. So it's manual or autonomous execution. So for all the access at the level 0, we have everything being done manually. So execution, awareness, analysis, decision, and the intent. Once you have all of them, plus the applicability, at all the scenarios, you have a level 5 network. This is the holy grail that I was talking before. So remember, I'm just yet another Indiana Jones looking for his holy grail of the full autonomous network. In most of the cases, telecom operators, I would like to make a guess. Everyone, please, eyes on the screen. And let me ask you, how many of you think that operators are at level 4, for example? I would like your hands on. up, if the hands up, if you think that operators are on level 4. No one. Okay. Let's see. Level 3. 2, 2, 3, 3. Okay, nice. 4. All right. And level 2. Now more. Okay, so level 2 and level 1. Okay, so it concentrates on level 2 mostly. You are almost certain. Most of the operators are between level 2 and level 3. That's true. And if I ask you for hyperscalers, what would you say? Like Google, Meta, and so on. Level 2? Level 3? Level 4? Something in between level 3 and level 4. Yeah, you are very right. This is how, how it is today. I was attending some internal seminars at Google. They will almost claim in level 4, but they are still missing a little bit of this predictive mechanism that I was talking about. But yes, you see, there's still a long journey to have a full autonomous network. So that's a good news, because all technicians means that we will have some job to do inside the operators and the hyperscalers in the next years. So the different challenges in achieving AN level 4, that's what typically the white paper talks about. It positions, okay, we are in level 3, we're almost there. What do we need to have as different challenges for having level 4? And one of them is about architectural complexity and integration. So you see that there is unclear evolution path. You describe a lot of CSPs struggle to define end-to-end layer 4 migration while maintaining service continuity. It's very difficult to have this migration path. Then to have integration challenges, all the new nice stuff that we have been researching on machine learning, LLMs, generative AI, digital twins, it's nice. It helps the 80% of the time, but this 20% is what is a challenge to integrate. So that's something that it still requires more effort. Then the organizational and operational challenges. These are the most difficult ones. These are not our business, but they are part of our business. So these operational silos, the human-machine collaboration, the skills gaps, all these organizational challenges are very important. And finally, we have the technology maturity gaps. Achieving this cross-domain orchestration, seamless automation across all the different network domains, it's difficult. It's still a challenge in some cases to have cognition, decision-making, and this having this context-aware, auditable AI across different scenarios. It's a hurdle. But with these all challenges, there are a lot of opportunities. Identified opportunities in the white paper are the business transformation opportunities, technical advancement opportunities. Of course, impacting autonomicity in the networks for the business is good. It provides accelerated service delivery. It reduces the operational cost. It accelerates innovation. Most of the benefits are already known from the programmability years, but with this new autonomicity layer, they become more and more evident. Also, these effectiveness metrics for AI and business impact. Technically speaking, we have a better customer experience, 0 downtimes. That's our challenge, to have this 99.9999999 ad eternum. To have network optimization and to also be able to scale more properly. So these are the different benefits. And what do we need to move from this level 3 to a level 4 using AI? So there are some of the things that we need: new AI capabilities, prediction. the capability not only to see what's happening and understand what's happening, but to predict the future, to make some decision making more cognitive based on the context, based on the status, the intents, and so on, not policy based or not rule based scenarios only, and to have cross-domain intelligence. Federated learning plus coordination plus agent-to-agent talking about the network. That's something that is still being under development. And then some of the implementation considerations, we need scenario-based rollouts. So we are starting to define which scenarios are the interesting ones, what do we need to make to expand them and to scale them. This is how we typically work at engineering level. We are trying to roll out all these scenarios. And then always keeping a human in the loop until you know this copilot stuff, and you know, okay, I would like to be able to handle my own car and to drive and to only be assisted. We have not reached yet the moment that we want to give away the steering wheel of the car and say, okay, please drive by myself in our network. This is something dangerous. We have still not built the trust on the system so that it can be completely run automatically. So this is very related with the risk and validation that I was talking about. And then there is another topic that is very important, is the governance and trust. Sorry. So which data is being used, what is kept with this privacy, where the decisions are taken, are we taking the decisions inside the operator, are we using models outside, where is the security, where we're protecting our data, are we doing it in the US way or in the European way? This is important, and also the scalability of the solution. So we see that level 4 enables these proactive, autonomous, and secure network operations, and it paves the work for the full autonomicity at level 5. So today I will be talking mostly, and it's not only me, but the white paper I'm presenting about 4 different enablers in the layer 4 framework. The first one is about network digital twins in autonomous networks. Digital network, at the time of today, I think that everyone in the room knows what a digital twin is, but I will present a little bit the concept and how this helps the layer 4 automation. Second topic, important topic, it didn't exist 3 years ago. So Gen AI for AN, how the large language scale models are able to help us in managing autonomicity in the network. Then I will be talking about agents, how we enable them, intent-based service creation and optimization of the 6G network. And finally, something that I like a lot, and everyone who knows me from the past knows that I push always, is the data models and APIs. So we need to have structural layers, we need to have a clear data model for this, and I will be showing you some of the work that we have been doing on that topic. So let's start with the network digital twins. So of course, it's a virtual replica of the network for safe modeling, simulation, and decision making. So these core capabilities are the predictive simulation, model updates, real-time telemetry, automation support for zero-touch ops, and many others. So you are seeing here the different loops that the network digital twin implies. So we have an actual physical network. There we have its own network digital twin. Of course, we provide the mapping. The network digital twin is able to provide feedback. On this, we have the entity training stage. Of course, this network digital twin needs to be trained with some of the data that comes from the actual physical layer. We can also train it with synthetic data from small scale testbeds. This training creates a model. The model is fit in the network digital twin, so it can be executed at a request for modeling different predictive scenarios or updates. So this is the behavior, and we have these pillars I have been talking about: the data ingestion from telemetry, sensors, history. Sorry. Then we have the AI analytics, that part of the model. We have the cloud native simulations, we have the closed loops, and more security. So the impact on the level 4 automation is that, for example, the decisions and closed loops allow us to have to forecast traffic and failures, to run what-if scenarios, to trigger auto reroute, repairs of the network, and support this intent-based execution. Continuous optimization helps us to tune the routes, the bandwidth, the configurations, and resources for higher QoS and efficiency, and learn from the feedback. This is very important. Then the testing suite. We have a playground for our network where we can do new traffic enrichment, we can redeploy stuff, we do performance benchmarking, we can also analyze what-if scenarios with fault injection, we can test security, which is important, then also do some regression, and all completely risk-free and very scalable. And some operator benefits. You have less downtime. You have your network virtual playground, and it allows you to have better utilization, to analyze and provide a stronger security. It provides higher autonomy, and just to mention that the digital twins that are being defined, for example, at ETSI, ISG, ZSM, are aligned twins that enable repeatable at scale validation and faster innovation. So we have seen the first pillar. Second pillar, generative AI for autonomous networks. The key benefits are very clear. We have natural language operations. We can have some chatbot. You all know the word. You all have been playing with chatbots lately. Please, I guess that most of you have done that clearly. And so you can have this conversational control, which simplifies, in theory. In my opinion, I don't see a clear benefit between using intent definitions or natural language definitions. To me, it's more useful if you have a data model for your request. But you can simplify complex tasks and boost human AI collaboration, which I think it's important. For me, it's more important the AI to AI collaboration. The adaptive intelligence handles novel conditions beyond rule sets. It handles more context-aware decisions. Then another of the benefits is the stronger assurance. It detects anomalies better. It also provides what is very important is the root cause analysis. Then it helps you to understand what is happening in your network, which is very interesting. It's a very interesting point. Typically, when something goes bad, there are hundreds of different alarms triggered, and to analyze this, to use an LLM is very, very useful. And then also one of the things that's very useful, an LLM, is the documentation. So please stop writing documentation. If you are programming, stop writing your documentation. Just use an LLM to analyze your code and to write the documentation. If you code properly, if your code is clear, code will be the documentation. So I guess that most of the programmers already know that, but if not, it's just a warning. I know now all the SDCs, they are just blaming Manel, Julian. I know, but code is the documentation, and this is the only way to go. I mean, I think that if you are all able to understand code, if you're not able to understand code, please use your LLM to understand the code itself. And if not, if the LLM is not able to understand the code, please, a mid-level programmer will also not be able to understand the code. I'm not being senior programmers, but please think on the people that are jumping in your organizations, make them the life easy, write some nice code without documentation, but nicely written. Then the continuous knowledge, auto-generated runbooks and configuration. This is important. Now, if you have your API, you have everything. You can go from a Swagger API directly to a full demonstration very quickly with generative AI. You can fulfill all the different configurations. Even you can also check some young models and easily write the different configuration setup for a small network. So all this stuff is a reality and a benefit for all our daily work. Still some challenges, the scale and latency. I mean, come on, we have limited windows. We need to count the different tokens that we're sending to our generative AI and so on. We have a lot of computation cost. Who pays for this? It's important. Now, most of the things are very subsidized because of the bubble of AI and all the different companies competing between them, but there will be one day that this cost will be computed in all our networks. Then there is still some domain gaps. We don't have a telecom networks LLM, general model. We can do some domain fine-tuning, we can do some RAG, and so on, but still some work to be done in this area. And this area is so quickly spreading that it's very difficult to follow. I mean, if you just look at IATF data models that are being generated every 3 months, you have new updates, you have new knowledge to be incorporated into your telecom LLM. So this will be one of the things that we will need to know how to mitigate. So let's see some of the applications for generative AI that the white paper proposes. I have put here that some of them. I recommend that you go through the paper. It's much nicer and much better explained than by myself. But let me just read a little bit about them. The predictive analytics and optimization. This is one of the applications, the what-if simulation, the synthetic data, capacity planning, this threshold, and so on. So this is one of the most important applications. The second one is about planning and design. So it's about topology auto-generating, capacity upgrades, options, trade-off, all these old stuff that was being done before, completely offline. Now we are bringing autonomicity and we're bringing it in operations. So this network planning goes to operations and it provides these capacity upgrade plans and trade-off analysis of the different solutions and equipment allocations. Then the self-healing. Remember, our objective is to reduce the MTTR to 0. So we need to detect subtle anomalies, propose remediation, and so on. If you ask me, this is done typically in the old-fashioned way of machine learning. Generative AI might play a role here in anomaly detection, but basically what's important is to analyze the trends and to analyze the data with machine learning stuff. Then security policy assistance. This helps to have real-time threat insights and draft rules and governance modes through all of them. And then the last ones, the intent-driven management, turn the business goals into policies, configurations, and QoS. Sorry. And finally, the automation acceleration, service templates, test cases, scripts, and documentation. So we have seen 2 of the 4 pillars for the level 4 autonomicity. The third pillar is, sorry, I need to take some water. it's very difficult to speak for more than half an hour without coughing. So sorry for that. Then, okay, here, AI agents. We all have learned about the agent stuff in the last year. It helps us a lot to go from intent to policy to action. The agents help us to translate the business and technical intents to all the different work that's needed below. They are able to be customized. There are some reference drivers. I recommend that you read the NCMN and ITU visions for this AI-enabled infrastructure. And the different operating model, all the stack view is important. We go from intent and dialogue, planning, execution, assurance, and governance. So where can the different AI agents be placed in operations? We can see that we have runtime control and QoS. They assemble the service graph on the fly, they integrate third-party functions, they dynamically tune the routing bandwidth, and they can help with the cross-domain policy. They can also help in operations, focusing on self-reflection and self-evolving. So this is where we include DRL on top of the agents, typically. So we have the agents that suggest different options. We evaluate the options, and we value the options if they are good or bad, and we do some enforcement of their capacity. So this self-evolution of the agents is very important. They are flexible to use for future proofing. They include security and safety by design, and they enable ultra-efficient operations. And the fourth pillar that I wanted to talk today about is the data models and APIs. So data models in autonomous networks, they provide a unified framework for representing the resources, the services, the intents, and operations, and enable consistent data exchange and intelligent automation across the diverse network environments. Different types of models that we might have are the network resource models. We have gazillions of them. I mean, go to ETSI, go to IETF, go to ITOT. You will find hundreds of network resource models. Service models, the same. TM forum and so on. So there are many different places where you will find them. Intent models. The window is reducing, but still you will find several of the different intents. But what happens with operational models? We don't have them. That's something that is missing. We need to cover management for data, for files, for performance and security. So these models will help us to build the foundation for the next autonomous networks, because they will model the different operations, they will model the different scenarios, and the different they will support the different use cases. So it's very important to focus on this. And also, when you have data models, you need APIs. In my opinion, one thing and the other are completely related, and they need to be closely work together. And the different APIs that are needed are management APIs, service APIs, and integration APIs. And of course, in there you see the different use cases for the data exchange. This is something that is needed. And with this, I end the first part of my talk. Now, I will start talking on what I have been discussing this and presenting this to you, because until now, half an hour, no TeraFlow at all. Let's go for there. What happens? This is a nice picture. Why do you need network automation? Because of this. Very quick and simple. I mean, how you fix this without automation, it's a nightmare. And of course, we can find ways of solving this. So first of all, let me sell a little bit what TeraFlowSDN is. most of you might know, so you can sleep for 5 minutes, and then I will come back to you, get all of you. First of all, TeraFlowSDN is a network automation framework. If I hear you saying TeraFlowSDN is an SDN controller, I will come and be very mad at you. TeraFlowSDN is something more than an SDN controller. Why that? Because SDN controllers only program your network. They are the foundation for everything else. But I like to position TeraFlowSDN as a full, complete network automation framework, because what you are doing, and you will see, is something far beyond network programmability only. So operators need automation. Automation means softwareization. That's why we're here. Remember that the first S of the conference is software. That's what we do. Networks are complex, so we apply software to solve our complex problems. And there are some specific domain solutions that can help us to automate our network. TeraFlowSDN is the first SDN controller, Mac network automation framework that provides cloud-native design. We have re-engineered what network controllers look like, and we have proposed a microservice-based architecture. So we allow horizontal scaling. We also are able to handle massive data streams. This is cloud-native way of doing things. So we are also by default auto-scalable and resilient. This is important. Come on. How you want to handle a tera of flows with a single instance of your code all plugged together in a single thread or a multi-thread, but in a single, let's say, how it was called? Well, you know what I mean. And finally, the flexi and easy deployment. We containerize our microservices, and we are native to Kubernetes to be able to run all our stuff. So I like to say, okay, these are our 3 X's of TeraFlowSDN currently for this network automation: programmability, observability, and security. So we try to be in the middle. So we provide flexible automation and policy-driven control. We enhance telemetry and real-time network visibility. And secure, we are able to start integration of quantum-safe security mechanisms and energy-aware slicing. So I recommend that if you are interested, you take a look at TeraFlowSDN code, and you take a look at the different partners that we are contributing to this. So this is our ecosystem. These are the different, we are in our leadership is Telefónica and Telenor, 2 operators. I like to say we are operator-driven by their request, their vision. That's important. And then technically speaking, these are the guys that are doing the real stuff, because I'm presenting it as an overview, but then there is a lot of technical work that's being done, being led by CTTC, but also with hundreds of contributions from Telefónica, UBTech, Kenit, and Chalmers. And then all the list of participants, as you can see below. But being in networks and in software is very difficult nowadays. There are many different places where decisions take place, where a community is contributing. So we are starting to engage with other communities. We have started to work, well, we have been working with OSM for 5 years, maybe, to support the different intercluster, interdata center view that OSM needs with TeraFlowSDN solutions for one infrastructure manager. We are contributing with OpenSlice, but you will get most of it tomorrow, so I don't want to spoil all the fun for tomorrow, people. Then We have the standards being defined in many different places. There is not a single place for standards. Sorry, I'm at ETSI, but I must say that this is not something that is only happening here. A lot of work is being happening, and basically the most interesting one, such as TeraFlowSDN, but also work also happens somewhere else, like IETF or the Linux Foundation. So we need to live in this multi-SDO wall. And last but not least, SDOs are not the only people in the play. We also have industry organizations. Telecom infrastructure project, for example, is an industry organization. Also OpenConfig. This was led by Google. Okay, we need to buy hundreds of routers, and we want Cisco and Juniper to fight between them so we can have the cheapest one. That's the meaning of OpenConfig, basically. So our ecosystem in terms of research, you see here lies on the left. You see the standards SDO that we are contributing, and on the right, the different research projects that have been contributing to TeraFlowSDN. The slide is up to date, but I guess that I hope that more contributions will come from the next round of SNS projects. Interfaces supported. Okay, TeraFlow is very nice, but can I play with it? I have a lot of equipment in my network. Can I plug it directly and run all the intelligence on top of it? So if you want this, you need to check our specs, and these are the different interfaces that are supported on top as the MBIs and on the south as SBIs. SBIs. We are proud to handle most of the significant network equipment. We are able to handle OpenConfig routers. This is very important. We are able to handle level 3 IP layer with support for most of the OpenConfig routers. We are able to support both netconf and CNMI versions of them, but we are also able to control underlying optical layers through the transport API. We are able to support P4 devices in compute networking using P4. We are able to support very nice features from Infinera, but this is something that it's quite outdated. And what's also important is the IETF ACTN models. On the MBI, the jewels of the crown are the layer 2 and the level 3 VPN service delivery. These are very important because this means that you can control your network, your layer 3 network or multi-layer IP or WDM network from the perspective of the operator using level 3 VPN service delivery. Of course, you can read the topology. We have an internal API and so on. That's something less important. Sorry, last but not least, the network slice service. This is very important because this is something that has been contributed lately. We have a network slice controller on top of it that is being able to support network slice definition by IETF. We have this was the latest contribution from the release 6 from Telefonica. We have aligned it and we have shown it to the project as a complete full module. You can use a network slice controller together with TeraFlow, but it's important to remark that if you are looking for a network slice controller, you can use it also outside TeraFlow. So it's an independent module that you can run internally with TeraFlow or with other world. In fact, the people from Telefonica, they are also providing some plugins for Nixia testing equipment. So please check on this. If your network slice controller rings you a bell, please check because this is very new and very useful. So this is the architecture I was referring when of TeraFlowSDN with the different components, microservices inside of it. I will not go into all the details because this is a nightmare. I will explain you what some of the things that and proof of concepts that we have done in relation with the different AI topics I have presented at the very beginning. So let's start with these twin girls and the network digital twin. So network digital twin, we have been working on network digital twins, I think that since 5 years ago. We have the definition here from ITF. And what I like a lot is that the definition of ZSM 015, digital twin, is the virtual replica of a real-world system, a physical system on which operations can be performed. The observed outcomes and effects of such operations constitute information that can be used, for example, to inform operational decision-making, including automating support closed loops. It's very important to say the digital twin is a replica, and the outcomes of a digital twin is information. So it's not decision, it's not action on the network. It's information about what can happen. It's very important because this helps us model better what a digital twin is and how we integrate it in our agents or how we integrate it in our network level, network autonomicity levels. So network digital twin is needed for achieving level 3, level 4, and level 5. You have already seen this paper, but from the perspective of how to apply it into transport networks, there are several works that we started in 22, and you can see that this was the first way. And one of the things that we also presented was one of the enablers for digital twins. One of the enablers is the data collection. So we take a look at how we could ingest data from a transport network. We were using a Kafka module. You will see an event source streaming mechanism inside the transport API. So this was something very, very innovative in 21. A lot has happened since then. I mean, at that point in time, we could not imagine what generative AI could be today. But at that point in time, we already knew that data was most of the significant keystones for the future. So this is one of the proof of concepts that we did with TeraFlowSDN in integration with OSM. We were reading data and the topology and the different connections from a network controller, and we were analyzing it. We were deploying through NFV Mano an instance of, I think it was at that point of time, Network X emulated, Container Lab, I think. And we emulated completely the network in using these emulators, network emulators. I think that the last we have done is with the optical mininet. And it helped us to predict some better routes for the network. So we were able to ingest the data and we were able to give feedback. So this end up in a proposition of different data model for lifecycle management of the entity. And I would like, this is not a draft any longer, but I would like to to give some minutes to discuss this figure because it's from ZSM 018. And it's very interesting to understand how an entity needs to be fitted in the whole line of thought, let's say, of a nation. This is something important. So we want an intent compliance assessor, which can be the one that invokes the entity base. So we need to comply with some intent. So we need to analyze scenarios. Okay, I trigger a new scenario with my entity. I analyze it. I have a solution, and then this solution needs to be applied to some control and decision mechanism. So the entity is not a controller, is not something that takes actions, decisions, is something that proposes solutions. We need another part of the mechanism that helps us to apply these solutions and check if they make sense. Other things that we have done in TeraFlowSDN about this. So what's tomorrow's forecast? It's okay. I have a 50% chance that I'm doing it. I'm going to get it right. No, forecasting is about checking the status of the network and being able to anticipate to network congestion, for example, and to predict demands on the future. Using machine learning, we have done a lot of this. We have an AI microservice pipeline, and we have also done some hybrid statistical and machine learning model. It's incredible when you have data and when you have a data scientist analyzing this data. You can do a lot of things. I'm just a programmer. I'm a telecommunications engineer. I'm not a data scientist. But if you have data, a lot of data, hundreds of data, and you have data science, you will see that some nice things can happen. And with Daniel, we have done some very nice work on traffic forecasting. So, for example, different applications on top of data. This is a computer network article. Also with something that was very nice to do. I don't know if you can imagine, but to use synthetic data to do predictions is even better than to use real data. That was something that was that we detected while doing some work on an optical network scenario for bear assessment. For the prediction, we did some synthetic genetic algorithms, which we detected that were able to condense the data information, and they were able to take better decisions and to run in less time. So, when you hear about using synthetic data, please always think that this might be a good way of applying ML to your network. So it was so good that we also created a mechanism for clustering the data and do some kind of cleanup of the data before doing predictions. And this got obtained the best paper award at IEEE and BSDN on 24. So you can see that the accuracy was better and the computational time was reduced. Then another of the things that we are preparing, and this will be shown at the next Mobile World Congress, together with Huawei, Telefónica, and Telenor, is the autonomous network as a service provisioning with AI orchestrated service migration for proactive SLA assurance in optical access and transport networks. So this, some of the highlights is, for the first time, we are introducing in our network predictive analytics. So we are not focusing on reacting, but on seeing what will happen in the future. We are closing the loop around it. And we are also introducing a cost-aware mechanism. So this predictive engine helps us to predict the future SLA risk based on the data on best effort at IP layer and access layer using FCA OTN. For that, we are using one of the enablers that is very significant, which is the SIMAP Young model for telemetry storage. That's something I will later come again. And now I have one demo, which I will not show because of the time. I have been talking for 1 hour and I still have a lot of slides to show you. So this is something that's on the web, on YouTube. It's a demo which shows how to scale up the deployment of a network digital twin. Typically, what happens is that networks are so huge that if you want to emulate the network, you need to some way of having a very large testbed. This for doing that. This is difficult, and we have what we have been doing is to play with different instances of parts of the network in AWS and interconnect them. So we have not a full virtual digital twin, but we have the digital twin with multiple Amazon Web Service instances are interconnected to them. So we are able to scale the network, because what happened was that we tried to emulate Telefónica's network, the transport network level 3 on Container Lab. Container Lab uses all the NOS, the different network operating systems, and it needs a lot of resources. This was impossible. So we engineered this way of scaling up a network emulation on the cloud. And this is the demo that we did, but I don't want to focus on this. So let's see what generative AI can help in TeraFlowSDN. So I found this very nice meme. I think that is very appropriate for this. I don't know how generative AI would respond to this intent. Maybe it's worth a try, how to apply the intent to the wall. But in any case, we have been doing a lot of research on intent-based networking and the relationship with generative AI. In XX2, we have presented what was the architecture for inter-based networking. And oh my God, sorry, you are getting my announcements. And the different tools for intent fulfillment, intent reporting, intent negotiation, intent SNA, we can see a lot of generative AI that can be applied, for example, in the intent translation, intent conflict detection resolution, intent feasibility check information, intent fulfillment information. So there are many different places where generative AI can play a role in intent-based networking. So what we did are several demonstrations and several proof of concept using TeraFlowSDN and generative AI in order to see how the different intents could be resolved. So in this case, we were providing intent-based networking for end-to-end packet optical cloud and native SDN orchestration. In this case, we were leveraging different generative AI for intent-based network operations in network slices. So in here, we had an LLM agent that offered this chatbot interface, which was fed with the information of TeraFlowSDN and also with the different intents. So when we were requesting an intent, you can see what happened on the chatbot conference, on the chatbot conversation between this and that. So that's what we have been doing and playing with generative AI and intents. So let me play this demo, which focuses on intent-based connectivity service provisioning with autonomous agent and TeraFlowSDN. So the motivation is clear. Our objective is to unify natural language processing, SDN, and LLMs. We presented this demo where we read the topology, where we emulated a network using Container Lab, as you can see here. Intent-based networking, we created a new intent-based networking request. For example, create a connectivity service from A to B with this quality and so on. And this was translated automatically into some of the different connectivity requests on top of TeraFlowSDN. So you see here, while we are writing the request using natural language, and this will be processed with the LLM and applied inside the TeraFlowSDN. So you see here that, for example, we are using the intent API from, I think this was from ETSI TFS. And you can see here how the intent has been created and how it has been translated into different endpoints, connectivity service endpoints, different quality request, and I think it was bandwidth. I'm not able to read it here, but you can check it in the video demo that's online. So then we check the logs and we saw it was applied. And then we go to TeraFlowSDN. This is how it looks like. You see the devices. And then you will see that these devices have been connected and the resources have been allocated to different networks. So see it here. It was here. So you see the service that has been created for this intent request. So we go from this connectivity to this translation of the slice on TeraFlowSDN. So this was the demo that we performed. I hope that you enjoy it. And also there are many others that you can check on the YouTube channel. So I will not go into detail of this predictive automation in intent-driven code-based service. And let me focus on the new topic. We had 4 wheels. We have seen 2 of them. The third one is agents, not better agent than 007. And let's see how we can use these agents to apply to our networks. So this is a proof of concept that we did together with Telefonica and IBM on how to apply an agent on top of TFS. This agent was able to read the network topology and both optical and packet layer, so Transport API and IETF. And it was being able to apply some of the different requests that were requested here. So in this case, we focus on security intents. So the different requests were about changing source and destination, changing interfaces, changing hierarchy, or at different layers. So this is what we obtain. Of course, using LLMs, you reach this 80-90% of accuracy that is usable, but not error-proofed for the 99.9% of the cases. Then other topics focused on traffic analysis. We have just published a journal on the topic, analyzing traffic and applying it to through an agent. So we were able to analyze traffic to classify requests and generate predictions with different models, and we evaluated them. Very interesting topic if you are looking for it in the networks. And the fourth pillar, it also it's important, and I think that we have done some interesting work. I was talking to you before about SciMap. SciMap is the service and infrastructure map. This is a key enabler from IETF for the foundations of a network digital twin. So you need to model to have a map of the service and the infrastructure. This map is designed to bridge the gap between the network layer and the service layer, and also enable integration with external models such as inventory, traffic engineering, and service assurance. This model allows the detailed topological representation and easy navigation between layers, which helps operators to manage the network and service information more effectively. The SciMap framework includes standard APIs for retrieving and writing data on topologies, supporting use cases like service placement feasibility, network simulation, capacity planning, and network design. So this is one of the foundations for the different data models that are needed for our digital twins. A lot of key benefits. I will not go through all of them, but just to let you know that we have been implementing this SciMap in TeraFlowSDN. There are some demos. In fact, the demo that we will be running at the Mobile World Congress will also include the SciMap implementation inside TeraFlowSDN. And another of the things that we have been doing is to expose optical network control capabilities using the model context protocol. So come on, if you have a REST API, you have an MCP server very quickly on top of this REST API. There are many different solutions to expose your Asian orchestrator piece of software which provides an API to another Asian, detail it with what it's able to do, and provide more autonomicity to your network. And that's something that we explored with the MCP server inside TeraFlowSDN to give 3 different primitives focused on the tools necessary for getting topology and understanding the topology, providing services, requesting services status, and providing intents. So these are the different tools that we defined with MCP, and they were provided to an agentic TFS agent to be able to request to different requests. So more work on this topic, you will see it in the future. Also with more focus on security, for example. So if we take a look at security, so just a nice meme about scams. It's me, yeah. You will see a lot of me right now, but I think it's interesting to say, okay, security needs to be by design, not because of someone doesn't check its email. So some of the challenges that we find in autonomous networks, and TeraFlowSDN is trying to play a role, is the cyber threats. There are many different the cyber threats, and we need to be able to stop them, detect them and stop them, secure the network digital twin and the agents. An agent taking control of your network can be a very dangerous thing, so we need to secure it. In this case, it's very important the work that SAI is doing inside ETSI, for example. Then the API security risks. Zero trust, don't trust anyone in your network, preserve the privacy AI. So there are a lot of AI techniques that help us to do that, to be GDPR compliant. And finally, to secure the generative AI, as I was explaining. So AutoSecOps is the way of doing this response, provide security evolution and intelligent security automation. That's something that's very important. Some of the work that we have been doing is to integrate the AI resources in the edge cloud and include GPU and TPUs in the network. We want to support SmartNIC integration, so we can use the SmartNICs to detect any kind of threat. If you introduce in-network computing with P4, for example, we are also able to do some threat anomaly detection at the network level. So these are the kind of things that we are looking inside TeraFlowSDN. One of the things was the integration of SmartNICs. In this case, it was a NVIDIA Bluefield 2 that was able to trigger an application to do threat analysis with all the traffic that was presented. Also, we have done work on traffic engineering and policy being done together with UBTech and based on P4 switches. And also to do some machine learning detection and monitoring using TeraFlowSDN. So I wanted to spend the last 10 minutes of my talk on the other topic. So as I said, AI can do a lot for networks, but networks can benefit a lot with AI. Sorry, AI can benefit a lot with networks. So if we take a look at AI, there are 2 different phases, training and inference. Training takes a lot of time. Learning phase, large data sets are processed, and then all the optimization is being done, but with these forward and backwards mechanisms, and the output is a trained model ready for deployment. The inference is different. It's during the execution phase we need to use these trained models from the previous phase to make predictions and decisions. The input is real-time data, and the process, the output is the prediction, the classification, or the action that need to be that need to happen. So they are different. We need to analyze how the AI traffic behaves in order to be able that the networks that we are building are being able to handle this AI traffic. So this is, as I've been saying, networks for AI. We have all what we have seen before. It was okay. AI is very funny and helps a lot into our networks, but this is the other way around. How networks pay back the help to AI to improve the connectivity and the data sharing between the different data centers that are training AI. The training shops inside the data center can generate terabits per second scale east-west traffic. All reduced and data shuffling is very intense, and the traffic is predictable, but with short bursts and latency sensitive. So it's in a special way. Our networks are not prepared and optimized for this kind of traffic. Inter-data center training provides a lot of bulk transfers. It is predictable, but highly variable in volume and geography. Some data center pairs might be quiet, others suddenly need multi-terabits per second for days. So the dynamicity is slow in the sense that dynamicity happens in hours and days. This means that, for example, doing this stuff at level 3 might not be the best solution. I'm an optical guy, and now I will try to explain you why doing some of this inter-data center training focusing on optical network transport is much better. For the inference, it is a little bit different. The traffic is much more dynamic from the milliseconds to minutes with spikes from crowds or daily patterns. So this is how the traffic looks like. If we analyze from the optical networks perspective, the requirements for intra-data center training are huge capacity and ultra-low latency. Then for inter-DC, elastic bandwidth and smart orchestration, remember that the delays are huge, so we can handle a network reconfiguration at the transport layer. And in inference, the requirements are others. They require deterministic low latency and ultra reliability. So the principles that we have AI-ready optical networks, we have been working on them for a long time, and optical networks are not just pipes, but right now with TeraFlowSDN, they are an intelligent adaptive infrastructure that enable this AI traffic. They provide awareness, they provide on-demand capacity, they provide assurance, they provide resilience, and they are AI native. So in this slide, it's very huge, and it provides a lot of different scenarios and the different traffic types and needs. I have summarized them before, so I will not go into details. But just to remind you of the principles that we have been discussing and how this AI management and optimization can be applied for optical networks. So in this view, we can have multiple edge clouds and interconnected and can help using federated learning towards the same training in the AI. Of course, all these can be handled using TeraFlowSDN. We can have this vision of a big central data center that connects a client directly to the AI mechanisms in the big data center, and the telecom networks only provide the traffic pipe, this intelligent traffic pipe, or a more complex scenario with distributed models that provide edge data centers where some of the training and inference is being done at the edge of the network. So with this model, operators could provide generative AI services towards the customers without exposing all the customer needs to third-party central data centers. So this could be an improvement for security, for energy, for survivability, and telecom resources. So let me conclude and let me just show you what we have been discussing today. I hope that you enjoyed a little bit the tutorial and how networks and AI can be related. So first things first, TeraFlowSDN is the reason I'm here, and it's the basis for network automation. If you need to control your network equipment, please come to us, say, hey guys, how can we manage this? We need a driver for this, how we can build a southbound interface for our equipment. We can help you with that. We are providing an intelligence layer on top of the network to fully exploit AI for networks. But not only that, but we are also contributing with handling the networks for optimizing the AI processes, which is what I have been presenting in the last minutes. This is a virtuous circle of innovation that it enables reference implementation for fast prototyping and feedback to the standardization community. And with that, and just some way of claim for joining our TeraFlowSDN community, I think I can conclude. So thank you very much for your attention during this hour.
Thank you very much, Ricard, for this very interesting tutorial where